Good morning, everyone. Thank you for joining us today. Welcome to the Deep Dive. We're kicking off an exciting new series today, Fundamentals of Internet of Things. And this first deep dive, well, it's an introduction to the Internet of Things. Now, if you've been with us, you'll probably remember our deep dives into the fundamentals of agentic AI. And what's truly fascinating, I think, is how these groundbreaking technologies, from the autonomous smarts of agentic AI to the vast connected fabric of the Internet of Things, are increasingly woven together. They're really shaping our future in some profound ways. So today, our mission really is to give you a comprehensive overview. We want to unpack IoT's core concepts, its evolution, the components, applications, and its future impact. It's all designed to provide those crucial aha moments, especially for you, our tech-savvy audience. To make sure we cover the landscape thoroughly, we're going to first lay out a roadmap. We'll list all the core questions we plan to tackle during this session. Here's what we'll be exploring. 1. To begin, can you provide a simple definition of the Internet of Things? 2. The concept of connecting devices isn't exactly new. So, what is considered one of the very first examples of an IoT device? 3. What key technological advancements had to happen for IoT to grow from, say, that single vending machine into the global phenomenon it is today? 4. You've mentioned an IoT system as a complex ecosystem. What are its 4 fundamental components? 5. Let's focus on the things for a sec. What's the difference between a sensor and an actuator? 6. What critical functions does an IoT gateway perform? Seems important. 7. The term machine-to-machine, or M2M, often pops up. How is IoT different from M2M? 8. And another related term, cyber-physical systems, or CPS. What distinguishes IoT from CPS? 9. Can you give some examples of how IoT is being applied in our daily lives, maybe in a smart home? 10. How is IoT being used on a larger scale? Thinking about smart cities here. 11. What about in healthcare? What exactly is the Internet of Medical Things? 12. Looking ahead, what key trends will shape the next wave of IoT innovation? 13. Now, while the future looks promising, what are the most significant challenges that really need to be addressed for IoT to reach its full potential? And finally, 14. To sort of wrap things up, what are the key takeaways we should all understand about the Internet of Things? Okay, that's our roadmap, so let's dive right into question 1. To kick us off, how would you define the Internet of Things simply?
Okay, simply put, at its core, the Internet of Things, or IoT, basically extends the Internet's power beyond, the usual suspects like computers and smartphones. It connects this vast array of other things, physical objects, processes, even whole environments. Now, these things, they're embedded with sensors, software, and other tech that lets them connect and exchange data over a network. And crucially, often without direct human interaction. It's essentially, it's the materialization of a world where our digital and physical realms are becoming intricately interwoven.
That really does sound like a monumental shift, creating, like you said, a global infrastructure. Okay, thinking about its origins, connecting devices isn't brand new. What's considered one of the very first examples of an IoT device?
Right, the conceptual seeds were planted surprisingly early. One of the first examples people point to goes way back to 1982. It was a modified Coca-Cola vending machine at Carnegie Mellon University. Programmers could actually connect to it using ARPANET, that was the Internet's precursor, to check if drinks were available, and importantly, if they were cold before making the trek over there.
Wow, a remote vending machine check in 1982. That's pretty amazing. It perfectly embodies that core idea, doesn't it? Getting information remotely from a physical thing. And if I recall, the actual term Internet of Things wasn't even coined until much later. 1999, I think, by Kevin Ashton at Procter & Gamble, looking at supply chains with RFID.
That's right. Kevin Ashton coined the term. His insight was really revolutionary for its time because back then, the Internet was almost entirely about human-generated data and communication.
Mm-hmm.
He proposed extending this connectivity to inanimate objects, giving them the ability to report their status, be tracked and managed by computers.
Mm-hmm.
It was about giving things a digital voice, essentially, to optimize processes like supply chains.
Giving things a digital voice. I like that. So, okay, getting from that single, albeit very clever vending machine to today's, global phenomenon that clearly required some massive technological leaps. What were the critical advancements that really enabled that growth?
It wasn't just one thing. The explosion of IoT we see now was truly catalyzed by a confluence of advancements, mostly in the early 21st century. Firstly, there was the miniaturization and proliferation of sensors. Big advances in MEMS technology, microelectromechanical systems meant sensors like accelerometers, gyroscopes, pressure sensors. They all got smaller, much more powerful, and drastically cheaper.
So the cost dropping was just as critical as the tech getting better, made it actually feasible to put them everywhere.
Exactly. Economic feasibility is huge for widespread adoption. Secondly, ubiquitous wireless connectivity became the norm. Widespread Wi-Fi, Bluetooth, and cellular networks maturing through 3G, 4G, and now 5G. And importantly for IoT, we also saw the emergence of low-power wide-area networks, LPWANs, things like LoRaWAN and NB-IoT. These are specifically designed for IoT needs, long range, but using minimal power, which is vital for battery-operated sensors.
Okay, so we can make cheap sensors, and we can connect them wirelessly pretty much anywhere. But once you have billions of devices sending data, what do you do with it all? That must have been the next hurdle.
That's absolutely right, and that's where the rise of cloud computing became absolutely critical. Scalable on-demand platforms, think Amazon AWS, Microsoft Azure, Google Cloud. They provided cost-effective solutions for storing, processing, and analyzing these just unprecedented volumes of big data coming from potentially billions of devices. Honestly, without the cloud, managing and making sense of that data deluge would have been practically impossible. It was a key catalyst.
And wasn't there also a fundamental limitation of the internet itself that needed solving? Something about addresses?
Yes, indeed. The IPv6 transition, this is crucial. The older standard, IPv4, only supported about 4.3 billion unique addresses, which sounds like a lot, but it's nowhere near enough for a world filled with billions upon billions of connected things. IPv6, with its practically limitless address space, we're talking 3.4 times 10 to the power of 38 addresses, completely remove that fundamental scaling barrier. So is this convergence, cheap sensors, ubiquitous connectivity, powerful cloud platforms, and enough IP addresses that really transformed IoT from a futuristic vision into the practical reality we see growing explosively today. It really was a perfect storm of innovation, wasn't it? Okay, so you mentioned an IoT system is like a complex ecosystem. Could you break down its 4 fundamental components for us? You use the analogy of a technological nervous system.
Yeah, that's a good way to think about it. An IoT system is typically built on 4 interdependent components, often visualized as layers. First, you have the things themselves, the sensors and actuators. This is the foundational layer. These are devices actually interacting with the physical world, collecting data, or performing actions.
Okay, the sensors and actuators are the hands and eyes out in the world. How does the information get back from them, and how do commands get out to them?
Right, that brings us to the second component, the gateways. These act as a bridge. They connect the things, which often use short-range or specialized communication protocols, to the wider internet and the cloud. Then third, you have the cloud. This is essentially the central nervous system. It's where the vast amounts of data are stored, processed, and analyzed, often using powerful software and algorithms.
And after all that analysis in the cloud, how do we as humans actually see the results or, control the system?
That's the fourth piece, the user interface, or UI. This is the point of interaction. It could be a dashboard on a computer, an app on your phone, maybe even a voice command system. It's how the insights from the cloud are made accessible and how users can manage or interact with the IoT system. Understanding how these 4 parts work together, things, gateways, cloud, UI, is really key to grasping how IoT captures data, turns it into actionable insights, and ultimately delivers value.
Makes sense. Let's focus on those things for a moment. We mentioned sensors and actuators. What's the core difference? If sensors are gathering info, what do actuators do?
Good question. So, sensors are like the sensory organs of an IoT system. They're the hardware components that detect and measure something about the physical environment. Temperature, humidity, motion, light, pressure, GPS location, chemical composition, even biometric data. They convert that physical property into a digital signal, providing the raw data. Think of the sensor in your smart thermostat measuring the room temperature, or a proximity sensor in a connected car. Actuators, on the other hand, are more like the motor functions or the muscles. They do the opposite. They take a digital command from the system and convert it into a physical action in the real world. So, turning on a light, adjusting a valve in a pipe, starting a motor, locking a door, sounding an alarm. Those are all actions performed by actuators based on commands, which are often derived from sensor data analysis.
Ah, okay. So using your smart irrigation example again.
Exactly. A moisture sensor collects data about the soil. That data goes up to the system, gets analyzed. If the system decides the soil is too dry, it sends a command down to an actuator, which might be connected to a valve, telling it to open and start watering. Together, sensors and actuators create this crucial feedback loop. The system can monitor the environment with sensors and then actively control or change it using actuators.
That feedback loop is really the heart of it, isn't it? Monitoring and controlling. Okay, so with potentially hundreds of these things out there, what critical functions does the IoT gateway perform? It sounds like more than just a simple bridge.
It absolutely is. It's a really critical piece of infrastructure, whether it's a physical hardware box or sometimes even software. It bridges the gap between the local things and the cloud or central network. It performs several vital functions. First, as you hinted, is data aggregation. A single gateway can collect data streams from many nearby sensors or devices, which might be using various low-power, short-range protocols like Bluetooth Low Energy, BLE, Zigbee, or Z-Wave.
So it consolidates data locally. But what if those devices are all speaking different languages, different protocols?
That leads right into its second key function, protocol translation. The gateway acts like a translator. It converts these device-specific or local network protocols into standard internet protocols that the cloud infrastructure understands, things like MQTT, CoAP, or standard HTTP. And thirdly, and this is really important for efficiency and responsiveness, it often performs data filtering and pre-processing. Sending every single raw data point from every sensor straight to the cloud can be incredibly wasteful in terms of bandwidth and can also add latency. So gateways often do some initial processing right there at the edge. They might filter out redundant readings, aggregate data over time, or maybe only send data upstream when a certain threshold is crossed or an alert condition is met.
That sounds like the foundation of edge computing, right? Doing some thinking closer to the data source.
Precisely. It reduces the load on the network and the cloud, and it allows for faster local responses in some cases. For instance, a gateway monitoring industrial machinery might analyze vibration data locally and only send an alert to the cloud if it exceeds a critical threshold indicating a potential failure. Saves a ton of unnecessary data transmission.
So it's an intelligent curator and translator for the data. Very important. Now let's talk terminology. The term machine-to-machine, or M2M, is often mentioned in the same breath as IoT. How is IoT actually different from M2M? They sound similar.
They are related, definitely. M2M is best understood as the direct precursor to IoT. Think of it as version 1.0, maybe. M2M typically refers to direct point-to-point communication between two or more machines. It's often isolated, purpose-built for a very specific task. Think of an ATM securely communicating with the bank's central computer, or a smart utility meter sending readings directly back to the utility provider. The communication is often over dedicated or proprietary networks, and the data is usually used for just that single specific application.
Okay, so M2M is more like a closed, private conversation for one specific job, whereas IoT is much bigger, more open.
Exactly. IoT represents an evolution and a massive expansion of the M2M concept. It's designed to be global and highly scalable, connecting potentially billions of diverse devices across countless different applications. And crucially, it does this using standard internet protocols, IP, leveraging the existing global internet infrastructure. Fundamentally, IoT is much more data-centric than traditional M2M. The primary goal isn't just point-to-point communication, it's about collecting vast and diverse data sets from a multitude of sources, aggregating that data in the cloud, and then applying analytics, machine learning, AI to generate new insights, enable new services, and optimize complex processes in ways that go far beyond the scope of a single M2M application. Think of a smart city. Again, it integrates data from traffic sensors, waste management systems, environmental monitors, public transport, all sorts of things to create a holistic operational view. That scale and integration is pure IoT, not M2M.
That scalability and the focus on data integration for broader insights really clarifies the distinction. Okay, another related term that comes up, especially in academic or industrial contexts, is cyber-physical systems, or CPS. How does that fit in? What distinguishes IoT from CPS?
Right. CPS, or cyber-physical systems, is often considered a broader concept, particularly strong in engineering and academic circles. CPS emphasizes the tight integration and feedback loops between computational elements, the cyber part, and physical processes, the physical part. The focus in CPS is often on high-precision control, reliability, and real-time interaction between the digital controls and the physical world. Think about systems where computers are directly controlling physical machinery with very tight tolerances and often safety-critical implications. Classic examples include things like autonomous vehicles, sophisticated robotic surgery systems, advanced industrial automation and control systems, or even something like the anti-lock braking system ABS in your car.
So the ABS system. Sensors detect wheel slip, the computer instantly calculates the right brake pressure adjustments, and actuators apply that pressure precisely, all in a fraction of a second. That's CPS.
Exactly. That tight, real-time, highly reliable sense-compute-actuate loop is characteristic of CPS.
So how does IoT relate? Does it overlap, or is it different?
There's definitely overlap.
Many IoT systems incorporate elements of CPS, especially when actuators are involved in controlling physical processes. However, the primary focus of IoT is often broader and perhaps less centered on that intricate, high-frequency, real-time control aspect. IoT is generally more data-centric on a macro scale. It's often about collecting vast amounts of data from many distributed sources, sending it to the cloud for analysis, pattern recognition, prediction, and generating broader operational insights or enabling new services, rather than just focusing on the immediate, fine-grained control of a specific physical process. So while an autonomous car uses IoT principles for communication and data gathering, its core driving control systems are classic CPS. IoT is perhaps more about the ecosystem, the large-scale data aggregation and analysis, while CPS often drills down into the specific, high-fidelity interaction between computation and a physical process. Does that distinction make sense?
Yes, that helps a lot. IoT is more about the network and the data insights at scale, while CPS is more about the tight, often real-time control loop between cyber and physical.
Got it. Okay, let's bring it down to earth, as I said earlier. How is IoT being applied in our daily lives? Maybe start with the smart home, since that's probably the most familiar example for many people.
The smart home is absolutely the most relatable entry point for most people. It's really about enhancing convenience, security, and energy efficiency in our living spaces. For energy management, you have smart thermostats. Google Nest is a well-known example. These devices learn your household's schedule and preferences, automatically adjusting heating and cooling to optimize comfort while aiming to reduce energy consumption. Studies suggest they can cut heating and cooling bills by, maybe 15–20% in some cases. Smart lighting systems like Philips Hue offer remote control, scheduling, ambient setting, and of course energy savings through LEDs and automated shutoffs.
And security is a big driver too, right? Lots of connected cameras and locks now. Definitely. For security and safety, you've got connected security cameras, smart locks you can control remotely, video doorbells like Ring that let you see who's at your door from your phone.
Yeah.
Then there are smart smoke and carbon monoxide detectors that don't just beep loudly. They send alerts directly to your smartphone and can potentially even notify emergency services automatically.
And for just making life easier.
Yeah, the convenience factor. Voice assistants like Amazon Alexa or Google Assistant often act as the central hub. You can use voice commands to control lights, thermostats, music, check the weather, set timers, even preheat some smart ovens now. It integrates control of many different devices.
It's really quite remarkable how quickly these things have become almost normal in many homes. Okay, moving beyond the individual home, how is IoT being used on a much larger scale, for instance, to create these smart cities we hear about? That seems like a huge, complex application.
It is a massive undertaking, but smart city initiatives are using IoT quite effectively to tackle the challenges of growing urbanization. The goals are usually to improve the quality of life for citizens, boost sustainability, and make city operations more efficient. A big area is intelligent traffic management. Cities are embedding sensors in roads or using camera feeds, combined with sensors in traffic lights, to monitor traffic flow in real time. This data allows systems to dynamically adjust traffic signal timings to ease congestion, maybe reroute traffic around accidents or events, and even provide drivers with real-time information on parking availability.
Okay, smoothing out traffic flow is huge. What about managing city resources, like waste or water?
Absolutely. For efficient resource management, you have things like smart waste bins. These bins have sensors inside that detect when they're full. This data is sent back to the waste management department, allowing them to optimize collection routes. Trucks only go where they're needed, which saves fuel, reduces emissions, and cuts operational costs.
Yeah.
Similarly, smart water meters deployed across the city network can help detect leaks much faster, both in the municipal pipes and potentially at the consumer end, helping to conserve precious water resources.
And public safety. Can IoT play a role there too?
Yes. For public safety, some cities are equipping connected streetlights, not just with efficient LED lighting, but also with additional sensors. These might monitor air quality, detect the sound of gunshots to alert police faster, or even serve as public Wi-Fi hotspots. It's about leveraging that existing infrastructure for multiple smart purposes.
The potential to optimize city living seems enormous. Let's shift focus again, this time to healthcare. What is the Internet of Medical Things, or IoMT, and how is it impacting patient care?
The Internet of Medical Things, or IoMT, is really about applying IoT principles, specifically within the healthcare domain, and is having a transformative effect, helping to shift healthcare from being purely reactive treating sickness towards being more proactive, predictive, and personalized. A major application area is remote patient monitoring. This is especially valuable for patients with chronic conditions like heart disease, diabetes, or respiratory illnesses. Wearable sensors, patches, watches, etc., or home-based devices can continuously monitor vital signs: heart rate, blood pressure, blood glucose levels, oxygen saturation, activity levels. This data is securely transmitted to healthcare providers, allowing them to monitor patients remotely, detect potential problems early, intervene before things get serious, and hopefully reduce hospital readmissions.
That ability for continuous monitoring outside the hospital must be game-changing for managing chronic illness. What about inside the hospital?
Inside smart hospitals, IoMT is also making a difference. For example, IoT sensors can be attached to critical mobile medical equipment, defibrillators, infusion pumps, wheelchairs. This allows staff to quickly locate needed equipment, improving efficiency, especially in emergencies. You also have things like smart hospital beds that can monitor a patient's movement, vital signs, and even whether the bed rails are up, automatically alerting nursing staff if there's a potential issue, like a patient at risk of falling getting out of bed.
And beyond the clinical setting, for general wellness.
Right. For personal wellness, the consumer wearables we see everywhere, Apple Watch, Fitbit, Garmin devices, are essentially part of the broader IoMT ecosystem. They empower individuals to track their own activity levels, sleep patterns, heart rate, and other health metrics, promoting healthier lifestyles and providing data that can sometimes be shared with doctors.
It seems IoMT touches everything from critical care to everyday fitness. Now, you mentioned cities and hospitals, but what about other major sectors? I know agriculture is huge, especially here in Canada. How is IoT impacting farming through precision agriculture?
That's a great point. Precision agriculture is a fantastic example of IoT delivering real value in a vital sector like farming, which is incredibly important for economies like Canada's. It's all about using technology to make farming more efficient, sustainable, and productive. One key aspect is crop monitoring. Farmers can deploy various IoT sensors across their fields. These sensors provide real-time data on critical factors like soil moisture levels, nutrient content, nitrogen, phosphorus, potassium, temperature, humidity, and local weather conditions. Armed with this granular data, farmers can make much more precise decisions about irrigation and fertilization, applying exactly the right amount of water or fertilizer only when and where it's needed. This drastically reduces waste of resources, cuts costs, and minimizes environmental runoff.
So it's moving from broad applications to highly targeted interventions based on real data from the field itself. What about managing livestock?
Yes, IoT is used there too. For livestock management, ranchers can use things like GPS-enabled ear tags or collars on their animals. These devices allow them to track the location of their herd across large pastures and also monitor animal behavior or vital signs that might indicate health issues. For instance, an alert could be triggered if an animal becomes unusually sedentary or strays too far from the herd, potentially indicating illness or danger.
And what about the farm machinery itself, tractors and such?
Absolutely. Automated machinery and drones are becoming increasingly common in precision agriculture, and IoT is key to connecting and coordinating them. You have connected tractors that use GPS and IoT connectivity for highly precise, autonomous navigation for planting, tilling, or harvesting, reducing fuel consumption and ensuring optimal field coverage. Drones equipped with specialized cameras like multispectral sensors can fly over fields and gather data that helps identify areas stressed by pests, disease, or nutrient deficiencies, often before these issues are visible to the human eye. This allows for very targeted treatment, again, saving resources and improving yields. It's really about transforming farming into a highly data-driven operation, maximizing productivity while minimizing the environmental footprint.
The impact across so many sectors is just staggering, and it really feels like we're still just scratching the surface. Looking towards the future then, what are some of the key trends you see shaping the next wave of IoT innovation? Where is this all heading?
You're right. We are still in the relatively early stages of this fundamental shift. Projections for the future are truly enormous. Some estimates suggest over 29 billion connected IoT devices by 2030, potentially driving over $10 trillion in annual economic value. Several key trends will fuel this. A major one is the convergence of IoT with artificial intelligence, AI, and 5G networks. 5G technology provides the ultra-low latency, high bandwidth, and capacity to reliably connect billions more devices, enabling more demanding real-time applications, think sophisticated autonomous vehicles communicating with each other in infrastructure, or real-time remote robotic control. And AI, particularly machine learning, is absolutely essential for making sense of the colossal data streams that IoT generates. It's what moves IoT beyond simple monitoring and reporting towards prediction, automation, and truly autonomous decision-making by the connected systems themselves.
This ties back nicely to our discussions on agentic AI, where systems perceive, reason, and act.
So AI provides the brains, 5G provides the super fast nervous system. What other major trends are emerging?
Another huge area is the continued rise of the industrial IoT, or IIoT. While consumer gadgets often get the headlines, many experts believe the largest economic impact of IoT will actually be in industrial sectors: manufacturing, energy, transportation, logistics. We're talking about creating smart factories where sensors predict machine failures before they happen, predictive maintenance, enabling self-optimizing supply chains that react dynamically to real-time conditions, and building intelligent power grids that manage energy distribution much more efficiently. And a third trend that's gaining a lot of traction, especially in industry, is the concept of digital twins.
Digital twins. Can you explain that a bit more?
Sure. A digital twin is essentially a dynamic virtual replica of real-world physical asset, process, or system. It could be a twin of a jet engine, a wind turbine, a factory floor, even an entire city. This virtual model is continuously updated with real-time operational data fed from the IoT sensors on its physical counterpart. The power here is that you can use the digital twin to run complex simulations, test different operating scenarios, predict potential failures, or optimize performance all in the virtual world without disrupting or risking the actual physical asset. It's an incredibly powerful tool for design, operations, and maintenance.
That predictive and simulation capability sounds incredibly valuable. But okay, while this future of interconnected intelligence looks very promising, it can't be all smooth sailing. What are the most significant challenges or hurdles that we need to overcome for IoT to truly reach its full potential?
You're absolutely right. Realizing this vision involves tackling some very significant challenges, and these need proactive and ongoing attention. Probably top of the list for many are security and privacy. Every single connected device, and remember, we're talking billions of them, often low cost and with limited processing power, becomes a potential entry point for cyber attacks. Securing this vast and diverse attack surface is a monumental task. Furthermore, these devices often collect vast amounts of data, some of which can be highly personal or sensitive, like health data from IoT devices or location data. This raises profound privacy concerns. We need robust security practices built in from the design stage, plus clear regulations, ethical guidelines, and user controls around data collection and usage.
Security and privacy are definitely paramount. What other major roadblocks exist?
Another significant challenge is interoperability and standards. The IoT landscape today is still quite fragmented. You have many different devices, platforms, and communication protocols from various vendors, and often they don't easily talk to each other. For IoT to deliver on its promise of seamlessly interconnected systems like a truly integrated smart city, we need much greater adoption of open standards and interoperability protocols so that devices and platforms from different manufacturers can communicate and work together effectively. Without that, we risk creating a lot of isolated data silos. And lastly, but critically important, is the issue of the digital divide. As IoT becomes increasingly integrated into essential services, healthcare, transportation, energy, even basic city services, there's a real risk of exacerbating existing inequalities. People or communities without affordable access to the necessary devices, connectivity, or the digital skills to use these technologies could be left behind. Ensuring equitable access, affordability, and digital literacy is vital if the benefits of IoT are to be shared widely.
Those are definitely major hurdles: security, privacy, getting everything to work together, and ensuring fairness. Addressing them requires a concerted effort from technologists, policymakers, and society. Okay, to bring everything together then, as we wrap up this introduction, what would you say are the absolute key takeaways we should understand about the Internet of Things?
Well, I think the first key takeaway is that IoT isn't just a futuristic buzzword anymore. It's evolved from a niche concept, like that Coke machine, into a powerful, tangible force driving significant transformation globally. Second, understand that it's a sophisticated ecosystem built on those four interdependent pillars: the sensor and actuator-equipped things interacting with the world, the communication gateways bridging the local and global networks, the analytical power of the cloud, and the user interfaces that make it all accessible and controllable. Third, remember its unique nature compared to its predecessors. IoT is fundamentally data-centric and massively scalable in a way that distinguishes it from point-to-point M2M. And while related to CPS, its focus is often broader, emphasizing large-scale data insights over just intricate real-time control. Fourth, appreciate its tangible and rapidly growing impact across incredibly diverse applications, from the convenience in our smart homes to the efficiency gains in smart cities and precision agriculture to the potential life-saving applications in connected healthcare via IoMT. And finally, perhaps most importantly, recognize that realizing the full positive potential of this powerful technology requires responsible stewardship. We must proactively address the significant challenges around security, privacy, interoperability, and equity to ensure we build a connected future that is both beneficial and just.
That's a fantastic summary. It really paints a picture of IoT as this fundamental shift, blurring the lines between the physical world we live in and the digital world of information. It's not just gadgets. It's like building a nervous system for our planet.
That's a great way to put it. A technological nervous system, allowing our environment and systems to sense, analyze, and respond more intelligently.
Exactly, making things more efficient, more sustainable, more attuned to our actual needs. But, as you stressed, this incredible potential comes with immense responsibility. We have to navigate those challenges, security, privacy, fairness, very carefully as we build this increasingly connected reality. The forward-looking promise, though, the really powerful idea, is maybe that of a world that can monitor its own health, optimize its own systems, and respond intelligently to the needs of everyone. Maybe, eventually, a truly sentient planet. It's a profound thought.
It certainly is. A lot to think about as this technology continues to evolve.
And speaking of evolution and diving deeper, be sure to tune in for our next installment in this series. We'll be getting into the nitty-gritty with Internet of Things architecture and design principles. So thank you so much for joining us today for this comprehensive deep dive into the introduction to the Internet of Things. We sincerely hope this session has provided you with valuable insights and maybe sparked some new ideas. If you enjoyed this deep dive and want to continue exploring the cutting edge of technology with us, please do remember to subscribe to our channel, Tech, AI, and Beyond. We look forward to having you with us next time.